Hi everyone, this is Jonathan Kirk, the instructor for MUS 370, and this screencast will cover the two chapters in our textbook related to ordered segments and how we can use this organization method of the matrix and of rows, serial rows, to look at both the compositions that are typical of this style, 12-tone pieces, but also see it as a compositional method or process that composers used, not only with the 12-tone method, which we associate with Schoenberg and Webern, but also composers like John Tavener, who used it in a more modal or tonal sense. So I refer to all of this as serialism, but we tend to use terminology related to order or ordered segments to describe the process that composers use to create this kind of music. Serial composition in general, it relies on order. So order matters, segments. That's just as important as listening to a melody, where if you were to take a melody that you know very well, flip it backwards, you probably wouldn't recognize it because you're so used to the order of those exact pitches. Well, serial composition relies on the same thing. So we refer to these ordered collections as segments. So in most cases, we think of serial pieces as relying on the 12-tone ordered collection, which we also call the aggregate. And when people mention serialism, that's usually what they think about. They think about the 12-tone row. But then again, it doesn't have to be the 12-tone row in terms of serial composition. You can make an ordered series of 5 notes, or even as simple as 3 notes. So this word segment is important. It refers to any ordered collection of notes. That is, the order of those notes is very important. So we've looked at John Tavener's The Lamb in class, and also the second movement of Anton von Webern's Variations for Piano. Two completely different works, but they rely on the same process of serialism. So ordered segments can be organized in a matrix, giving them different permutations, those 4 different permutation types that we talked about in class. And we'll get to that in a second. So just so we understand that serialism is a method of organization, and it's mostly related to pitch organization, although composers in the past have used serial techniques to order rhythms, dynamics, and even tempos. So going back to John Tavener's work, The Lamb, we can see that here he's using an ordered segment of 7 pitches to generate all of the other segments from that. In this case, we look at this melody here, Give Thee Clothing of Delight, and we see that this segment here, and he's put a little dotted bar line here, that this segment yields all of these other segments. We can see that this segment here, we'll call our prime segment or our prime row, is exactly the same here. It's just in reverse. We call this retrograde. We take the same segment and we flip it upside down. We call the mirror inversion, and this is exactly the same as the method of inversion that we did with pitch class sets. We start it with B flat, so this inverts on the B flat axis here. So up a major third here, B flat, down a major third here, down a major second here, up a major second, and so forth. So what's heard here is the inversion of the ordered intervals of our segment. So we have that, we have our retrograde, and we have this inverted row, and then we have this over here, which is the inverted row in reverse. So you can see that this segment is exactly the same as this segment, but it's in reverse. So we call this the inversion. Sorry, we call this the retrograde, this the inversion, and this the retrograde inversion. So serial composition will use these 4 types of permutations on an ordered segment. First, we can take the original ordered segment and we can transpose it however many times are possible. So in 12-tone music, that means we can take a prime row and transpose it 11 times. That gives us 12 transpositions. So inversions are essentially those ordered segments, they're just flipped, where the pitch interval of the prime rows is the same, but it's in reverse order, or we just simply use the word inverted. Retrograde, same thing with the prime rows, we just hear them in reverse, and the retrograde inversion, here we have the inverted rows in reverse. And we label these PRI and RI, standing for prime, retrograde inversion, and retrograde inversion. So it should be brought up like in class. There is something confusing, and this has to do with the two different ways that we label these permutations. And we're going to look at a matrix that actually shows you both ways of doing that here in a second, but I just wanted to point this out as it came up in class. So one method is to label each row, and you label it prime and then a number. And that number, the one way to do it is make that number the first pitch class. So for example, a P7 is a row or a segment P that begins with pitch class 7. So that's referring to, in this case, G. So any ordered segment, prime ordered segment that starts with G is P7. That would work the same for retrograde. But remember, in this case, R7 and P7 are not, they're different rows, right? R7 is a segment R, retrograde row, that begins with PC7. So that would be a row that begins with G. So you'll note that this is different from the other method that we'll look at. So you use this method, and this is the method that Elizabeth Marvin encourages you to use in the book. The other way to do it is to refer to the specific transposition of the row. And this is the one that I happen to favor. Although I think both are perfectly fine, you just want to make sure that you're consistent when you're analyzing this music so that you don't confuse these two labeling methods. So, for example, this second method is given a prime row, let's say P0, which is our original row. And 0 means that it's not any transposition of it. So if you were to transpose that by one semitone, we would label that as P1. So P1 is essentially T1, the transposition 1 of P0. And that works the same for all other permutations. And what's good about this system is that if you have P1, then R1 is going to be the same row in reverse. So that number will refer to both the prime row and the retrograde row. And that works for inversion and retrograde inversion. So give an example of a prime row P0. The retrograde inversion 5 is that retrograde inverted row transposed up 5 semitones. Okay, so let's talk about what we do when we are working with a 12-tone row. And I'm going to give you Webern's row from Opus 27. It's the variations for piano. We've looked at the second movement. And I'm giving them to you in integers, 4, 5, 1, 3, 0, 2, 8, 9, 10, 6, 7, and 11. You'll notice that this is our row. It has no repetitions. This is the aggregate. It's every single chromatic pitch that we have. And the order of this is very important. So we can use this order to build a matrix, which we'll look at in just a second. There is always some confusion when looking at a piece of music that is a 12-tone serial piece, because you might not know what the actual prime row is. That's not necessarily important. What's important is that you're working with at least some row that is related to this intervallic content. So this row, we could call it P0, but it could also be I6. Either way, you're going to get the same 48 permutations, right? So we'll never know unless Webern essentially told us that this was the row that he's using as the prime row, and that's really doesn't have any musical significance, because it's the relationship between the rows that I think that matters mostly, not necessarily the row itself. There's lots of ways that you can analyze the row. Because we have 12 pitches, it's very nice to break up into even parts. For instance, you could break it up into 4 trichords. You could break it up into 2 hexachords. You could break it up into 6 dyads. And you could break it up into 3 tetrachords. So here, you'll probably want to do all of those types of divisions of the row just to see how the composer came up with this row. In this case, Webern is really crafty here. If you separate it into 4 trichords, you'll notice that each trichord, so 4, 5, 1, that's one trichord, has an instance of interval class 1, heard as a minor second. The next one here is 3, 0, 2. You can see 2 and 3 give you that minor second, interval class 1. 8, 9, 10, you can see interval class 1 right here. And 6, 7, 11, and interval class between 6 and 7. So that's nice. Each trichord has this instance of interval class 1. Also, the prime forms are really interesting too. You can see that there's a pattern here, 012, 013, 014, 015. So where one trichord has 2 instances of interval class 1, the other has an instance of interval class 2, the other one has an instance of interval class 3, and an instance of interval class 4. So it's a really interesting way that Webern came up with this row form. And of course, if you split it in half, the 2 hexachords, they're entirely chromatic, and they share the same prime form. And looking at that, splitting it in half, you'll see that one hexachord is the first 6 notes of the chromatic scale, starting with C, and the second hexachord is the remaining 6 notes of our aggregate. Here's another row form that I always found really interesting. This is from Webern's Opus 24. It's really amazing that he found this perfectly symmetrical way to divide this row form. You'll notice in terms of its prime forms, it's all the same. So you have the minor second or interval class 1, and then you have interval class 4 here. So it's a minor second and a major third. So what he did is he found 4 trichords that all show exactly the same interval content. And of course that will divide evenly in half too. So this is really a wonderful row that Webern is working with in his Opus 24. So the 12-tone rows that we have looked at in class are interesting because we can see how composers use this technique to create some really interesting structures. So the 12-tone row is one that we spent the most time on. It's probably the most complex, and it's probably the most widely known in terms of how it's used in this technique of serialism. So serial music composed with the aggregate, or 12 pitch class segments, we usually refer to that as 12-tone music or dodecaphonic music. Arnold Schoenberg, the originator of this technique, and his 2 students, Webern and Berg, are the most well-known serial composers. However, they're also known for writing wonderful tonal compositions too. And dodecaphonic music relies on this matrix for pitch organization. So many of the early serial composers who became interested in this became interested in row forms that would create a matrix that had duplications in it. And we call this type of duplication invariance, because I think if you have a matrix that has 48 unique permutations, it's from a compositional point of view, it's too much. I think composers tend to like restrictions and working with these restrictions so that they can better organize their music. Let's look at kind of how this works in terms of its structure. This is a poem that is dated from the Middle Ages that Webern was really interested in, and you can see that it shows numerous types of organizations with the same words. So sator, arepo, tenet, opera, rotus can be read in all of the 4 permutations. It can be read forward, it can be read backwards, sator, arepo, tenet, and so forth. It can be read inverted, sator, arepo, tenet, opera, rotas, and it can be read in the retrograde inversion too. So forward, backwards, up, and inverted. So let's talk about the row matrix quickly. Much of your analysis of 12-tone serial music is going to look for PC orders that are generated from each of the rows. So once you've determined the order of the row pitch classes, you're going to label them, label their placement in the chords by giving them order numbers. So you can usually just write the number of the note, its order number, on the score. And for the analysis project, you'll see that's what I'll ask you to do for this short Dalla Piccola piece. Now, if orders are hard to find, say you have the matrix and say, well, I just don't see the row, that could be a possibility of combinatoriality. Now, combinatoriality is when two forms of the same row are paired, so that that the row's initial hexachords, when combined, complete the aggregate. So where one hexachord from one row and another hexachord from another row come together and make a unique row. This is something that Schoenberg was really interested in doing, and it certainly makes for a more interesting use of the matrix. Now let's look at the matrix itself. How do we come about this this magic square, as Schoenberg called it? Here I've given you the Opus 27 matrix. This is thought to be the row form that he used in all three movements: E, F, D flat, E flat, C, D, A flat, A, B flat, G flat, G, and B. We've looked at this one in class. This is our prime row. I'm going to use our labeling system that says this is the original row, P0, meaning it's the original transposition, whereas the first transposition, up a semitone, would be here. And I found that because I look for a semitone above F, which is F, and then I label this P1. You'll notice that this row here is exactly one semitone higher than our prime row. Now, if we go up a half step to G flat right here, that will give us, whoops, no, go back, there we go. That will give us our row form transposed up two semitones. So we label that P2 and so forth. So once we get that, we can see our transpositions, we can do it that way. But you'll also see that we can't do that unless we invert the row first. So this is the inversion row. So in every matrix, the prime row will be up on top. The inverted row will be the first column. So this will be the first row. This will be essentially the prime column. We call this inversion. So E to F, E goes up a half step to F, E goes down a half step to E flat. So you follow the interval of each pitch and you just do the opposite here. So this is how we invert the row. I can show you that there's an easier way to think about inversion if we use the clock face, and that's it here. So I'm going to note that this prime row starts with E. It's very important. You'll notice that that E stretches through the diagonal of our matrix, but also we're going to use that as the point of inversion. It's the axis of inversion. We're going to invert on the axis of the beginning pitch, which is E. So you simply draw a line through your clock face, which goes right to B flat, which is 10, and you'll see that each element now has its inverted pair looking across from itself. So F inverts to E flat and vice versa. E flat inverts to F. D inverts to F sharp, and F sharp inverts to D. So going back to our matrix, you can see that D is 1, 2, 3, 4, 5, 6. It's our sixth note in the prime form. 1, 2, 3, 4, 5, 6. There it is, see? So that is the inversion of this, and vice versa. G flat inverts to D, and if you look here, here's our G flat. That will invert to D over here because it's the 10th note of the order, 10th note of the order. So that's how this works. You cannot go wrong with this method. It's a quick and easy way to invert your row. You could certainly do it the old-fashioned way by looking at the interval class between each note, but this is really a nice visual way of thinking about inversion. Now here is another. This is Elizabeth Marvin's version of the matrix. It's the same matrix, but she actually lists the prime row as something different. That's not a big deal because if you go back to see that our original row here, which actually goes E, F, D flat, right? We're looking for 4, 5, and 1. We see that here she listed it as 4, 5, 1, 3, right here is R11. That's not going to change our matrix too much. The relationships are going to be the same, but what does change is the labeling system. Now, remember I told you that now we're using a labeling system where the prime row, the numbers are given for their first beginning pitch class. So P2, see, is the row that starts with 2. Now notice that if you go to the retrograde version here, even though it still calls it retrograde 2, this is an aberration in the online matrix generator. Just know that in Elizabeth Marvin's system, this would be called R7 and not R2. This is using two methods to label the matrix. That can be confusing, but just make sure if you keep both of them straight, you'll know that what we're referring to. And I'll also show you an example of how invariance will come up in a matrix. So you'll see that all of these pitches here in red, these hexachords are all combined together. They're all the same pitches. The order is different, but 0, 4, 5, 1, 2, 3 and 0, 4, 5, 1, 2, 3. You can see that this pitch collection is shared between rows. So here RI6, R11, they share exactly the same pitches in their first hexachords. So this is an example of invariance that I mentioned earlier. So a little bit about how this is used in the compositions in terms of style. So Webern's Opus 27, the variations, the second movement, which we looked at, is really interesting because it focuses on this kind of classical binary form. In fact, we even thought that it might be related to rounded binary form. It also uses something that's unique. It uses repetition. We usually don't think of serialism and repetition being reconcilable, but certainly Webern finds a way to do that, especially in many different ways in this piece. And so that's something that's very interesting in terms of its style. And also the extreme registral changes. That's something that really is interesting about Webern's Opus 27. Webern also elides rows together. So where is an example where a row form would complete and the last pitch class is going to serve as the first pitch class for a new row form, much like a phrase elision that we've seen in tonal music. So this is something that's interested in the style of Webern's works. And also this thing that we refer to as registral invariance, and this is really, really cool about the second movement of Opus 27. So over half of the pitch classes in Webern's row appear in one and only one register, so they're frozen there. And that's something that you might not hear until you've actually really listened to it several times, or you've looked at the score and you've done a careful analysis of it. And it gives this idea of the pitches being kind of frozen in register, or kind of being fixed there. It really presents a very interesting way to listen to this piece once you've gotten to know it pretty well.